trends in ionization energy. Ionization energy is the energy required to remove a ground state electron from a gaseous atom or ion. We do it in the gas phase to remove other effects. This energy differs when we deal with a bulk phase ion, solid atom. When we remove the first electron from an atom, a neutral atom, that's called the first ionization energy. But we can do a second or a third or a fourth ionization energy also. So for ionization energy, a low ionization energy means it's easy to remove the electron, easy to turn it into a cation. A high ionization energy means it's hard to remove the electron, hard to turn the atom into a cation. So these are the values of ionization energies for most of the elements. And you can see there's some structure in here, and we'll discuss this structure, these trends that we see. So the first ionization energy, this is what we'll start off talking about, is first ionization energy. It's the energy required to move an electron from a neutral atom in the gas phase. So we're creating a +1 ion, +1 cation from the neutral atom. So our trends, we have two general trends. So if we look at a column, such as the noble gases here, we see that the ionization increases as we go up the column. So it's not a linear trend here, but it's still an increase as we go up the column. So high in the column, helium has the highest ionization energy. Low in the column, radon has the lowest ionization energy. We look at the alkali metals, and the trend is still present. It's not as dramatic, but the highest ionization energy is for lithium, top of the column, and lowest ionization energy is for cesium at the bottom of the column. So ionization energy is highest on top of each column and lowest at the bottom of each column. The other trend, for which we do have some exceptions, is that as we go left to right across a row or period on the periodic table, we are increasing the ionization energy as we go from left to right. So we see that the alkali metals have the lowest ionization energy and the noble gases have the highest ionization energies. And we do see that there are some steps on this trend, some exceptions to this trend, and we will look at those exceptions also. So these exceptions, these discontinuities in the ionization energy. So using period 3 here, we put in 2 electrons and then it drops. So after you do 2 electrons, we have filled the S sublevel, and the drop is for the first electron on the P sublevel. So when we complete a sublevel, the next electron will be lower. But we have another discontinuity over here. But we haven't completed the P sublevel, so we put in our first P, second, third, fourth, fifth, sixth. So our discontinuity occurs after we put in our third electron into the P sublevel. That is when we have 1 electron in each orbital. Spin paired, not spin parallel, so all the spins are parallel, spin up, but 1 electron spin parallel in each orbital. And then the next electron, this is the first electron that is now spin paired, doubled up in one orbital. So we have a little electron-electron repulsion going on when we pair up our electrons in an orbital. So when we have a half-filled sublevel, this is stable, so it takes a bit of energy to remove the electron, and then the first electron beyond the half-filled sublevel. Now this electron is breaking the spin parallel that we have with the 3 parallel spins, and it has a little electron-electron repulsion going on, so it's not as stable, so it's easier to remove. So we have a little dip after we complete a sublevel and put the first electron to the new sublevel. We also have a little dip after we half fill a sublevel and put a new electron into that first paired electron into that sublevel. So we see the filled S sublevels on period 2 and period 3 is obvious. We lose it beyond that. But on period 2 and period 3, we are seeing a dip after we complete our S sublevel. After we fill the P sublevel, half fill the P sublevel, so we put 3 electrons into the P sublevel, the 4th electron creates a dip on period 2, on period 3, and then on period 4 it becomes almost equal. So period 2 and 3 are the most obvious for both completing the S and half filling the P sublevels. Filling the D orbital also. So we're seeing the D orbital in period 4, starting from period 4, and we see a big drop. After we complete D, our first electron on P is a noticeable drop. So we continue that trend here, period 4, period 5, period 6. Well, combining these two, the red circles and the blue circles. So after we fill S, we start the P. After we fill D, we start the P. So the trend that the P sublevel is a decrease in ionization energy follows for all the periods. So the first P electron is a decrease in ionization energy for period 2, 3, 4, 5, and 6. So we're seeing this throughout all the periods that our first P electron is a decrease in ionization energy over the one before that. And we do see additional structure in here in the D level. The D electrons tend to move around with the S electrons, so there's a lot of movements going on. So this is a little bit more difficult to explain with a simple explanation, and we would have to do more modeling, computer modeling, to fully show the shifts in energy throughout these D levels. But we see that the first P electron is always a decrease over the column before it, whether it's S or D. And the fourth P electron is a true decrease over the third, the half-filled shell, for period 2 and period 3. We can look at successive ionization energies, so second, third, and fourth ionization energies. So second ionization energies, ionization energy to remove an electron from a +1 cation. So we're taking +1 cation in the gas phase, removing an electron to form a +2 cation. The general trend is that the second ionization energy is going to be larger than the first ionization energy. So it takes more energy to remove the second electron than it does the first. So for a set of elements here, for one full row, we see that we go from 400 kilojoules per mole to 4,000 for sodium, 700 to 1,400 for magnesium, 500 to 800 for aluminum, 700 1,600 for silicon, 1,000 to 1,900 for phosphorus, 1,000 to 2,200 for sulfur, 1,200 to 2,300 for chlorine, and 1,500 to 2,700 for argon. So the second one is always higher than the first one. And this trend will continue, so the third ionization energy is going to be higher than the second. The fourth is going to be higher than the third. The fifth is higher than the fourth. So as you increase successive ionization energies, it always gets harder to remove that next electron. But if we look at one particular atom, any particular atom, or if we look at one particular atom, we're going to see increase, 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 and then at some point, the magnitude of the increase jumps tremendously. So for that same row, if we plot these ionization energies, the sodium one becomes dramatic increase after the second ionization, at the second ionization energy. Magnesium is a third. Aluminum is a fourth, silicon is a fifth, phosphorus is a sixth, sulfur is a seventh. So the trend on this one, not there. The trend on this one is that after we remove all the valence electrons, the outer shell electrons, when we remove an inner shell electron, is a dramatic increase in ionization energy. So since only sodium has one valence electron, that's relatively easy to remove. The second one is an inner shell, so that becomes a dramatic increase. Magnesium has two valence electrons. Those two are relatively easy to remove. The third one is inner shell, so it becomes dramatic increase. So all these high peaks are the inner shell electrons. So for sulfur, sulfur has 6 valence electrons. There's a smooth trend in increasing the ionization energy, removing those. The 7th electron is an inner shell electron, so that becomes a dramatic increase in energy to remove the 7th electron, the inner shell electron.